Chapter number 7 of linear integrated circuits. We are going to discuss about oscillators and waveform generators. So what are oscillators and waveform generators? Basically, these are circuits that produce an oscillatory output, a periodic output in the shape of oscillations of most of the time a square or rectangular waveform. There are some oscillators that produce sinusoidal waveform, but there are very few of them. In this chapter, the one that we are going to look at specifically will be either a square wave generator or a rectangular wave generator. The difference between a square wave and rectangular wave, from my point of view, is that a square wave has 50% duty cycle. That is, it is high 50% of the time and low 50% of the time. Whereas rectangular waveform generators are they do not have 50% duty cycle, either less than 50% or more than 50%. So in this chapter we're going to start with the basic idea of how to create an oscillator using operational amplifier, and then we are going to look at 555 timer IC, which is perhaps one of the most commonly used IC to produce a timing circuit, oscillatory circuit, clock circuits for digital ICs, and so on and so forth. So let's start this chapter. There are two ways to produce oscillations. We are going to look at specifically the first one, which is the timing method. And the timing method basically uses your RC circuit, like we studied in circuit analysis. It uses a timing method. It uses timing of RC circuit, and using that timing method, it produces oscillations, as you will see very soon. And the other one is the unity loop gain method, where you can still produce oscillations at the output if you maintain the gain of the amplifier to be 1. We are not going to look at this method right now in our discussion. The first method will be discussed. So oscillators in technical terms are called multivibrators. That is, it can vibrate between multiple levels. You have discussed multivibrators in digital systems. For example, flip-flops are multivibrators. They can either produce a 1 or a 0 based on the status of their clock. If the clock, which can be either positive going transition or negative going transition, they can activate at any of the transition based on what type of flip-flop you're using. But when they are changing, the clock is changing its level, then the output of a flip-flop can also change based on the other inputs of the flip-flop. So flip-flops are bistable vibrators. That is, their output can be low or high, and both states are stable. They can stay in that state as long as the condition at the input is not going to change. Now there are some monostable vibrators, multivibrators, for which only one state is a stable state. And again, in digital systems, we discussed one-shot circuits, in digital systems 2 specifically. And one-shot circuits is an example of monostable multivibrators. That is, only one state is stable. It will stay in the unstable state for a specific period of time, but then it's going to return back to its stable state. And then the third type of the multivibrators that we are going to study, which are basically oscillators, are astable. That is, none of the state is stable. It keeps vibrating between high state and low state. So those are oscillators, and that's the one that we are going to discuss in this chapter. So first we're going to look at the basic idea behind an operational amplifier, astable multivibrator. So look at this circuit. All the multivibrators and oscillator, generally they have a positive feedback. That is, the feedback from the output going to the non-inverting input terminal. As you saw in the comparator circuits as well, we used to have positive feedback. So this is basically, they are basically derived from the comparator circuits. Now, the difference between this one and comparator circuits is that they include the timing oscillators include a capacitor in series with a resistor. So they are in series. Of course, they are in series. Why? Because we know that no current goes in the terminals of the operational amplifier. So this is 0. So basically, capacitor, resistor, and the output voltage, they appear in series with each other, and that's what we are going to discuss actually, as how the voltage across capacitor is going to change with this circuit. So this is your output voltage, V out. This is your resistor, which is this resistor, and this is your capacitor. And then this capacitor voltage, Vc, is basically the voltage at where the inverting input terminal. So this is V negative T. And remember, whatever voltage we have at the non-inverting terminal, if this voltage is greater than the inverting terminal voltage, then the output is going to be in the positive saturation mode, right, as we discussed in the last chapter. And basically Vd, remember the differential voltage, will be greater than 0 if the V positive T is greater than V negative T, and Vd will be negative if this voltage V negative T is greater than this voltage, or the voltage across capacitor is greater than this voltage. And for those values, of course, the output will have the negative saturation. So the output will still have two levels, Vsat and negative Vsat. And these two levels will depend upon if the capacitor voltage is greater than V positive T or less than V positive T, right? It's very straightforward. So let's see how we can analyze what the capacitor voltage will be at what time and what is V positive T. So V positive T is simply V out. Let's just look at the diagram. So V positive T here, again these two resistors will appear to be in series because no current is going to go here. So V positive T is the same voltage as across V2. So this is V positive T across V2, right? And that voltage, of course, is going to be V out. So V positive T equals V out R2 over R1 plus R2. That's using voltage division, right? Now, when the output voltage will have Vset, then of course replace V out by Vset, and the V positive T the voltage at V positive T is going to be Vset R2 over R1 plus R2, and we are calling this voltage V1. That's the threshold voltage. And when the output voltage is negative Vset, of course this is going to be negative V1. That's a negative threshold voltage. Alright, so now capacitor is going to charge and discharge. Now remember, since the voltage at this point will either be V1 or negative V1, that means if capacitor voltage is greater than V1, the output will be negative Vset. So as soon as output is gonna go to, so let's say that this voltage is V1. Let's start like that. Let's say this voltage is V1, right? And capacitor is charging. As soon as capacitor voltage will exceed this voltage V1, then the output, which was at Vset, because this voltage is V1, is going to switch to negative Vset, right? Because the capacitor voltage will just become greater than this voltage. So once again, let's assume output is at Vset, right? Output is at Vset. So this is output, and your V positive T, the non-inverting voltage, is going to be V1 at that time. And capacitor is charging. Now why capacitor is charging, we're gonna discuss pretty soon. So let's say capacitor is charging from some voltage to towards V1, let's say, or going beyond V1, as you will see. But as soon as capacitor charge is going to reach V1 and exceed just a tiny bit, what tiny bit is that? 64 microvolt, as you remember from the last chapter. So it will exceed 64 microvolt beyond V1, then VD is gonna become negative, or VD is going to basically become negative enough to change the output to negative Vset, right? So it's gonna go to negative Vset. Now as soon as it's gonna go to negative Vset, V1 is gonna go to negative V1, right? Alright, so now Vset becomes negative Vset. So capacitor voltage, which is at V1, which was at V1, will start discharging now, right? Will start discharging now, and we're gonna study the math pretty soon. And when it will be discharging, when it starts discharging, it will still be higher than V positive T, because V positive T is now at negative negative V1. So now it starts discharging from V1. So when it is discharging, as soon as it will become equals to negative V1 and then becomes a little bit lower than negative V1, then VD is gonna become positive again, right? Because this voltage is gonna become less than the non-inverting voltage. Inverting voltage will become less than the non-inverting voltage. As soon as that will happen, the output is gonna go back to V saturation, and this will become what? V1. Now this voltage was at what? Negative V1 at this time. So now it start charging back towards V1, and this cycle will keep on going. So let's go and show you this. I just discussed this circuit right here, the same circuit. So this is what's going to happen. The capacitor voltage will be comprised of two components, right? So let's say, let's assume that as we discussed, let me show you the circuit type, this one. So this is what we discussed, right? So capacitor voltage is going to charge from negative V1 to positive V1 to negative V1 to positive V1. Because why? Because when it is charging from negative V1 to positive V1, the non-inverting voltage is at V1, right? Because the output has jumped to Vset. So when it is going towards V1, going towards Vset basically, and in that process it's going to reach to V1, and as soon as it will exceed V1 by 65 microvolt, then this voltage V negative T becomes greater than V positive T, and the output goes to negative V saturation. And as soon as output goes to negative V saturation, V positive T goes to negative V1. And then this start discharging. As soon as it goes to negative V1 and become negative 65 microvolt smaller than that, the output instantaneously go back to positive Vset, and this goes back to positive V1. And then it start charging again. So these are the waveform. So let's look at the math real quick. So the capacitor voltage, which is the voltage at the inverting terminal, is comprised of, from circuit analysis, two components: a steady state component and a natural component. And we can write that steady state component as Vset. Remember, how did we used to find the steady state component? Basically, you let the voltage run for the longest time, and the capacitor will be fully charged eventually and become open circuit, and whatever voltage that will appear across the capacitor at that time, that is considered as the steady state voltage. So if this output is at Vset and we let this circuit run for the longest time, of course the capacitor will be completely charged and holding the voltage Vset. Now that voltage will not occur, but for the equation, that is the value we are going to use for the steady state voltage. That if we let this circuit run for the longest time, then since the input voltage, the output voltage, which is the input of this RC circuit, is Vset, Vset voltage will appear across the capacitor. So the steady state voltage is Vset, and the natural component is always, it's an exponential component. For the first order circuit is a e to the power negative t over tau, where tau is the time constant of the circuit, which we know is RC. And remember, what is the time constant of the circuit, of an RC circuit? Time constant of an RC or RL circuit basically deals with the natural response of the circuit. What is the natural, when the natural response happens? When there is no external source in the circuit, and capacitor voltage, or capacitor if it's an RC circuit, or inductor if it's an RL circuit, capacitor and inductor are acting as sources, and they are providing energy to the circuit. So what is the time constant again? The time constant is the time that in which the capacitor voltage charge drops down to 36% of its maximum charge or maximum value. So that's one time constant. Alright, so this is the natural component, and we need to know what is the value of A. A is unknown over here. How are we going to find A? Using the initial conditions. Alright, so the initial condition mean what was the voltage across capacitor at 0 positive. Remember, 0 positive, 0 negative we used to use in circuit analysis, which means just after, since capacitor voltage cannot change instantaneously, whatever voltage was just before the change happened, the change is happening at a reference voltage, a reference time of 0. So whatever voltage just before the change, that is at 0 negative, stays the same as the voltage just after the change, which is at 0 positive. So first we're gonna see what was the voltage across capacitor just before the change happened, that is just before the output output basically move to Vset. So in this case we are assuming that output is at Vset, of course, that's why the steady state value of capacitor is Vset. And when output is Vset, remember V positive, T is V1, right? So just before the output moved to Vset and V positive T becomes V1, what was the value of the capacitor voltage? And we know that value of the capacitor voltage was negative V1, right? Negative V1, because when it reached to negative V1, in this cycle you can see it clearly, when it reached to negative V1 and just become negative 65 microvolt, which we assume to be 0, just become less than that, the output switched to V1, right? The output at that instant switched to V1. So the initial value on the capacitor voltage was negative V1. The initial value on the capacitor voltage was negative V1. So we're gonna go ahead and plug that value in this equation when we evaluate this equation at 0 positive. So Vc 0 positive is negative V1, and from that, by plugging in those values, negative V1 is equal to Vset plus A, e to the power 0 becomes 1, so A will be negative V1 minus Vset. And that will be the equation of the capacitor voltage when it is charging from negative Vset, negative V1 going towards Vset. Okay. So capacitor voltage will start charging toward Vset, but as I discussed, as soon as it will exceed V1, that is V0 positive will become less than V0 negative, and output will switch to Vset. Negative Vset, sorry, this is negative right here. Negative Vset, right? So as soon as it reaches to this point, now if of course we let it charge, it's gonna go eventually to Vset, which will be the steady state value, but it cannot, because as soon as it will exceed this value, then the output is going to switch to negative Vset, and since output is the input waveform for the capacitor, then instead of Vset value, its value will become negative Vset, right? So now capacitor voltage will be greater than this voltage actually. So capacitor will start discharging. Okay, so that's what it is explained over here. So when it will become greater than V1, the output will switch to negative Vset, V positive will become negative V1, and capacitor will start discharging towards negative V set. And once again, as soon as it will become less than negative V1, again V positive will become greater than V negative, and the output will switch to V set, and this cycle will keep on going. So this is how the circuit is operating in detail. I explained it to you. Think about it a little bit more. Okay, so to determine what is the time period of the output waveform, to determine the time period of the output waveform, we use the equation of the capacitor voltage. VCT is equal to the one that we discussed right here. VCT is equal to V set minus V1. Okay, so we will substitute T is equal to T1. T1 is the time at which, this time T1, at which the output goes from high to low, right? So at this time, right, at this time the capacitor voltage was V1, as you can see, right? So at this time the capacitor voltage was V1. So we go ahead and substitute that time over here, negative T1 over tau, and then we will solve this. E negative T1 over tau is going to be this, and then we take the natural log of both sides to find T1, and T1 is going to be tau natural log of V set plus V1 divided by V set minus V1. Now we assume that T1 is half of the time period because the time constant is same for both charging and discharging, so it's going to take the same amount of time to charge to V1 and then to discharge to negative V1 for the capacitor when the conditions are changing, output conditions are changing. So the time period is going to be twice the amount of T1, which is 2 tau natural log of that, and then we go ahead and we substitute the value of tau. So tau is RC, and then we go ahead and we'll substitute the value of substitute the value of V1 from 7.1. As we know that 7.1 is when we were calculating the value of, what is the value of the positive voltage right here. Let me go and remind you. Oh, too far. Right here, this voltage V1. So when this is V1, output is R2 over R1 plus R2 V set, and when this is negative V1, output is R2 over R1 plus R2 negative V set. So we go ahead and substitute that value over there as well, right here in this equation. So we change the value of V1 to V set R2 over R1 plus R2, and then we will simplify it, and this is the result that you are going to get, which is in front of you right here. So when you're designing this type of circuit, generally what we do is we basically choose R2 to be 0.86 times R1, and when we do that, natural log of this quantity becomes 1, right? Natural log of this quantity becomes 1 if we choose this. So let's say if we choose R1 to be equal to 10 kilo ohm, then R2 will be equal to 8.6 kilo ohm, and if we do that, then natural log of this quantity is going to become 1. So it will be easier for us to design the circuit in that case. We can choose either the value of C or R and then find the other component for a specific value of time period. So if we do that, our time period is going to be 2 tau, which is 2 RC. So let's look at example 1. This circuit is given to you. It's an example from your book actually. So V1 is called feedback voltage. I think I did not mention it, but it is called feedback voltage. So that's your V1. So it is asking you what is the feedback voltage corresponding to this circuit, and feedback voltage, saturation voltage is given to you 13 volt. Again, I did not put it, but saturation voltage is 13 volt and negative 13 volt, which in most of the exercises book is taking positive negative 13 volt. Okay, so 13 volt and then simple simplification, and 5.2 volt is the feedback voltage. So anytime your capacitor voltage is going to exceed 5.2 volt, the output will switch to negative V saturation, and as long as the capacitor voltage is less than 5.2 volt, the output will be positive saturation. Time period, again we calculate the time period using the equation that we have above, and simple put down the values, calculate the time period, and of course the output frequency will be 1 over time period. And look at this example. Design an astable multivibrator with the output frequency to be 10 kilohertz and the feedback voltage is positive negative 13 volt. So as I mentioned earlier, it will be easy for you to design if you stick with this relationship, so that your natural log of this is going to become 1. So R1 we take 10 kilo ohm, R2 we take 8.6 kilo ohm to satisfy this relationship, and let's assume C is 10 nanofarad. So the time period basically becomes 2 times RC, or 2 times tau, and from that we can calculate R to be T over 2C, which came out to be 5 kilo. And for this, feedback voltage is approximately 6 volt, 6.01 volt. And in the next video we're going to discuss 555 timer.